morning, students.
Good morning, ma'am.
Good morning, ma'am. Good morning, ma'am.
What I observed is very few of you have tried the first experiment. I received, I think, 7 to 8 files. What about others? Why you have not uploaded others? Make on
Ma'am,
uploaded.
my proteus isn't working exactly. I'm still trying to make it run.
Shamni. What
Yes,
about
ma'am.
Shubhamni, Snehal, Parth? I think one of the Parth has uploaded. I don't know exactly Parth Kulkarni or Gulwani. So tomorrow is the last date. If you are facing any problem, you can ask me. I'm ready to help you. Only 5 experiments. I think only 4 to 5 we can implement. Other I have to only give you demo. Okay. So you can put your problems. You can just share your problems after this experiment. Okay. We will start with our second experiment. And as you know, our second experiment is Arduino. That means we are trying to obtain the roll, pitch, and yaw. Okay, actually yaw is not possible because it's a rotation about z-axis. Okay, so that is not possible. And whatever write-ups I have shared in that, it is mentioned ADXL335 accelerometer, which consists of only accelerometer. It is not having gyroscope built on that. Okay, give us the basically what is accelerometer is, it is nothing but it's a motion sensor. It is able to sense the displacement or movement in x, y, and z direction. Okay, so this is what ADXL335. There are various accelerometer, gyroscope, and combination of these two ICs are existing. Okay, for example, this ADXL335 is the accelerometer module, which is simplest to use. Okay, it is very straightforward. It has something, it looks like this, okay, which has 5 pins, output pins, in which 2 are required to supply, to give power supply to this particular board, okay, this chip, and 3 are directly corresponding to x, y, and z displacement. Okay, basically accelerometer will sense the acceleration in a particular direction. Okay, but this acceleration usually we measure in terms of meter per second square, whereas here that displacement or the that acceleration is given in terms of g unit, gravitational unit. Okay, and hence whatever is x, y, z values we are getting, that will be in terms of gravitational units. Those are not directly acceleration, or that is not in terms of meter per second square. Okay, so you need to convert that into the required unit. Okay, and from those 3 values we can find out the rotational angle, the tilt angle for a particular object. And for that the formulas are already mentioned here. So basically these values are the analog values we are getting, and those analog, this part is giving you just mapping your analog values to the digital values, that is in the range of 0 to 5. Okay, so this is what this portion is giving you, conversion of analog to digital. Okay, and this 1.65 and 330 millivolts, so it is representing the sensitivity, and the voltage level at 0g is represented by that. At 0 gravity it is 1.65 is existing, so that much voltage we are removing from whatever we have obtaining. Okay, that will be subtracted, and it will be usually to get that x value. Okay, so our actual this meter per second square value of this x direction, y direction, we need to divide that raw value or the converted value by its sensitivity. And the sensitivity for this ADXL335 is mentioned as 330 millivolts per G. Okay, so the G is gravitational unit. Okay, so it is that is how we are converting our actual analog value or whatever is the raw value that is obtained from the sensor, that will be converted into the required unit. Okay, once we have that, we can convert those values into raw, pitch, and roll in these values, okay, using these formulas. So it is simply nothing but conversion of just mapping those values into the angular speed. Okay, so using the geometry, that is, we are using tan inverse and z and y and z for calculating. We are considering y and z components. Okay, and that is how we can obtain roll, pitch, and yaw. Okay, the same thing is represented in the same formulas are used. I'll simply explain you this code, because what the components I have purchased, that I have just ordered MPU6050, not ADXL335. Okay, so ADXL335, as whatever the just documents I read, so this is it can be used to obtain roll, yaw, and pitch, but MPU6050, it's a combination of your accelerometer as well as gyroscope, which is resulting into very accurate values. Okay, and that is why I just purchased this one, and I have currently with me MPU6050, which is the accelerometer and gyroscope. It's a combination of both. Okay, so we will perform our experiment on that, but as write-up is having ADXL, I'll explain you the code of ADXL also. It works similar to your MPU6050. Okay, so very simple code. ADXL is very simple to use. Okay, other, if you are going for ADXL345, it uses I2C interface to connect your chip with the controller. It requires I2C bus for communication, whereas here it is straightforward. We can directly use 3 output pins, which can be just connected to the which are connected to 3 analog pins, A1, A2, A3, or you can use any analog pin. Okay, so those are set to read your analog input from the sensor. And as I explained you the values, so these are the commands to get those analog values: X out, Y out, Z out. We are reading will be assigned to this X ADC value, Y ADC value, and those ADC values are converted into digital using this particular formula. Actually, you can write here 1020. That means it's a 10-bit ADC. So where the maximum we are just your ADC values can be mapped in the range of 0 to 5. V reference is 5. So it will be mapped in the range of 0 to 5. Okay. And in that, the zero gravitational voltage will be subtracted and it is divided by the sensitivity. Okay, so these are giving us the acceleration in X, Y, and Z direction, and using those values, now using the geometry of this, okay, X, Y, Z geometry, we can obtain the angular displacement, that is rotation about X axis is known as roll. Rotation about y-axis is known as pitch. As rotation about y-axis is pitch, to calculate this pitch, we are considering x and z component, not y component. Whereas here for roll, we are considering y and z components. Okay, and here it will be x and y components to calculate yaw. Okay, and the same values are displayed. This code is very straightforward. Okay. So there are no complications, but I cannot show you execution of this code because I don't have that ADXL335. Okay, whereas we are going for another another sensor, which is nothing but MPU6050. Okay, which is a combination of accelerometer as well as gyroscope. I'll show you the internal structure of this. Are you able to see the screen? Yes, students?
Yes, ma'am.
So this is the internal structure of your MPU6050. Okay, so basically it gives us the 3 values corresponding to accelerometer, 3 values corresponding to gyroscope. Okay, and ADC conversion is done within the chip itself, and that will be processed, and this is representing your I2C interface. That is also existing within this, and communication is done through the I2C bus. I2C bus means we are using this serial clock and serial data pins. This is to connect your auxiliary external external IC or external chip to this MPU. To communicate with the external chip, these auxiliary pins are used. Okay, whereas we are using only these two, interrupt and VCC and ground, for connecting your MPU. Apart from 3 accelerometer readings, 3 gyroscope, it has inbuilt temperature sensor also. Okay, so that means we can get the value of temperature sensor. Now, another thing you should know is all these values are obtained, are stored in the register, sensor register, in the form of 2's complement. Okay, and hence whenever we are actually we want to display that, again we need to convert that value into 2's complement. We have to obtain the 2's complement divided by the sensitivity as we have done there. Okay, the sensitivity corresponding to accelerometer gyroscope is mentioned in the corresponding data sheets. We have to use those values. Usually this requires 16-bit. Okay, and hence 16384 is the sensitivity for accelerometers, and for gyroscope it should be in terms of the angle. So that sensitivity is 131 per degree centigrade. Okay, so that is the sensitivity of this gyroscope, and that raw value obtained needs to be divided by that sensitivity. Okay, and the communication is done through this sensor register, through this I2C interface to the controller that you are connecting. Okay, so it will be the connection diagram I'll show you here. Okay, so we are using this interface, okay, where VCC and ground are required, the supply to this chip are required. Okay, so as I said, there are 2 inputs we are using from this, is this is serial clock and serial data. Okay, those serial clock and serial data are connected to the A0 and A1, A4 and A5 here. I have connected those 2. I'll just check. Yeah, I have connected those 2, A4 and A5. Okay, so the analog pins A4 and A5, the same thing. Okay, and we need to get interrupt. Actually, interrupt is required. I'll show you 2 different versions of this code. One is very easy to understand, and another one is representing how exactly it will be used for the motion detection. Okay, how it is calculating the rho. So actually calculation we are not able to understand from that code. So for understanding calculations, I will explain you this code, which is very easy to understand. And the second code that we'll observe is just to check the processing, how the object can detect the motion through this processing software. Okay. So I'll first show you. As I said, this requires I2C communication bus. Okay, MPU60, even your ADXL345 accelerometer, which gives you only 3 outputs, that is corresponding to acceleration in direction of X, Y, and Z. Okay, so same way here, this MPU6050, this chip is giving me 6 outputs, basically 7 outputs. Okay, 3 accelerometers, 3 gyroscope output, and 1 is corresponding to your temperature. And all these values we can obtain through the I2C bus, where every value will be first placed in the sensor register, as I think I have shown you this. It will be placed in the sensor register, and from the sensor register through I2C serial interface, it can be obtained. So based on the clock frequency, it can be obtained on the serial data, where we need to decide the initial address for this MPU in the code, and at that particular register, we can obtain the values. Okay. So here it is MPU address is we are passing. So what is the MPU address? You need to set that MPU address, the serial register value where you want to store on your Arduino. So usually it will be hex 68. Okay. So this is, you need to initialize first this address. Okay. You need to initialize these variables to get the values from that serial input. Okay, and for that, for I2C, you need this header file. Whenever you are using I2C interface, whatever may be your application, so to execute that, to implement that, you need this wire.h header file, which is representing I2C communication protocol, or which is used to implement I2C. Okay, so I2C uses basically 2 wires communication. Okay, serial clock and serial data. So 2 wire interface. In this setup, as I said, setup is used to initialize all your peripherals. So here we are initializing our I2C first and then serial monitor. So I2C wire.begin, begin transmission, start transmission, whatever is the data stored at this location can be read, and we are reading from that location, writing into this 6B. Okay, so 0. This is how we started that one, and in loop. Okay, so begin transmission from this again, that is initially we have set those register. Okay, again we are starting here in loop. Now it is continuously transmitting data from the 6 inputs. Okay, so every time we are reading new value, we have to just begin the transmission, get the address and whatever is the value at that address. Okay, so store that value in the corresponding register, write that value into this 3B. Okay, in transmission false, only one value we are reading, then again it is false, so that it cannot read or write the existing value. Okay, so this will be just said request is true, and we are trying to just write that one. So what exactly, this is also again important statement that you need to understand. So wire.read, then this is representing your left shift by 8 bits or wire.read. Okay, so once the transmission has been started, okay, we are reading the values at a particular register. As I said, it is using 16-bit, the values are 16-bit 2's complement form. Okay, whereas your Arduino register consists of only 8-bit. Okay, so whatever is the current value we have read, we need to shift it by 8 position and add or that particular value with the current value, that is LSB will be read first. That LSB value is shifted by 8-bit position, and then MSB is read first, and that is shifted by 8-bit position, and then we are adding the LSB in that. So this is how we can get the actual value of that accelerometer x direction, and then converting it into this is what mapping it on the minimum and maximum values. Okay, so this is something we are converting it into the required range. Okay, and this is just converting that into the obtaining angles, that is nothing but obtaining roll, pitch and yaw. Instead of roll, pitch, yaw, here directly it is represented by x, y and z. Okay, so is that clear? This is very simple, only accelerometer is used similar to your ADXL335, and this will give us the clear idea how we are getting the roll, pitch and yaw. I'll show you the interfacing. I'll just switch on my video, and then we'll execute this code, and I'll show you the readings on this monitor. So this is, I cannot zoom actually this one. Are you able to see the video?
Yes, ma'am.
Okay, so this is the chip. I have mounted that on this breadboard. I fixed it, and we are using serial clock, serial data, VCC ground, and that is connected to your Arduino. Okay, so basically connection.
Ma'am, you are not audible.
Ma'am, you're not audible.
So interrupt pin we are using as 2. Okay. Now I'll execute this code, the code that I have explained you. Okay, done uploading. I'll show you the serial monitor. This baud rate is 9600. Okay, so this is the simple code where we are getting this angle X is nothing but roll, pitch and yaw. Okay, actually I wanted to show you now video how we are rotating that one. Are you able to see this camera video?
Yes, ma'am.
Yes, ma'am.
Can I simultaneously switch on this COM port? Yes. Okay. See now my breadboard is horizontal. So this direction, in this direction we are getting. No, actually I hold this like this. Okay. So in this direction, X is representing, this is Y, okay, and Z we cannot represent. So currently your Y, as it is parallel to Y, you're getting Y as almost 1, okay. So I'll move this around X axis, okay. I'll hold this something like this. Actually we have moved this around Y axis, okay. And you can just see here the roll had changed to 290. As I'm holding this, the values are not stable. Okay, again then move it around y-axis in another direction. The angle had changed. It is now 81. Now same thing I'll show you with this is, it is taking as x as 0. Okay, now it has become stable. X is 0. Okay, this is the correct position actually I'm now holding. It is something horizontal. Okay, so you can just observe here. It is our this breadboard is parallel to our XY axis. Okay, and as I said, it gives you the gravitational unit or G force. So G force is acting on the Z axis. Okay, and Z force is acting on Z axis. We are getting, this is representing rotation about Z axis. Okay, if I hold it, if I just put it on the surface, you will get 1 1 for X and Y. Okay, that is almost 0. 359 is almost 0 degrees, 360 degrees, and this is also representing 0 degrees. So rotation about X and Y is 0, whereas you're getting maximum rotation around Z. But if I move that, now I'm just moving this sensor around X axis. So this rotation is known as around X axis, and you can see now the values of angle X is changed. It is very sensitive, needs to be stable to get constant values. So this is representing rotation around X axis, that is roll value has changed. I'll just rotate that in the opposite direction. Okay, so now you can observe we have just obtained that as 70. Okay, so this is how we can get the rotation or roll and pitch. Okay, now the same thing I'll represent using another code. I'll just stop this one. Any doubt in this? Okay, is that clear? So we can get the angle around x-axis, angle around y-axis, z-axis not able to show. Okay, but it is changing according to the position of that. Now this is very clear from the processing software. Okay, I'll just explain you that code first. Whatever is possible from my side, I'll explain you because most of the things are directly given there. So it's a ready-made example in the MPU6050 library. You might have observed here for this particular whatever XYZ angles we have calculated using this MPU, that doesn't require you any library. It will use the wire.h, which is the inbuilt library. Whereas for using this particular code, you need to install, you need to copy two libraries. One is I2C device library, that is this I2C communication protocol library from the dev, I2C dev. We are copying into the Arduino's library folder, as well as we are copying this MPU60 library into that Arduino's library folder, and that you can find at this particular link. Okay, the link is also given in this, and here actually various they have given, after installing, actually you can find under examples, you can find that MPU6050 motion sensor library is added, and you can find the examples, and from that example we are using this code. Okay, DMP6. DMP stands for digital motion processor, which is part of your this IC, MPU6050 IC. Okay, you can find we need to include that header file I2C dev for I2C communication. Okay, and again we need to use wire.h header file. Okay, so that is also required, and instead of MPU6050.h, we are using this MPU6050_6 axis motion, 6 axis motion, that is 6 readings we are obtaining, apps 20.h. Actually, as I said, this is the example, it is the ready-made example we can find under this MPU6050 examples. Okay, and in this, now this is the variable that we have set for MPU6050, and various macros has been defined. So this is one macro where we are getting the direct readings obtained from the sensor. Okay, this is another macro where they are giving the these readings in the form of Euler angle. Okay, and this is the macro in which we are interested, yaw, pitch and roll. Okay, so we need to uncomment that the corresponding macro so as to get the required output, and this is the third one. Okay, so this is readable real acceleration. Okay, only accelerations we are getting, the raw values corresponding to acceleration, and readable world acceleration. I don't know exactly what is, I have not tested actually these two. Okay, we are using this yaw, pitch and roll, and this one is the macro that we are using for processing software, and from that processing software the working of this accelerometer will be clear to you. Okay, so whatever else I can explain, I'll explain from this code. So this is for only for self-testing. Inbuilt LED has been set. Okay, so these are all the variables, those are required for processing the values. Okay, so these are the variables represented to get the raw values corresponding to each macro. Okay, so it is generalized code, and this is an array which is used to get again the values and used to operate our processing simulation. Okay, so in setup we are similar to that one. Within macro, actually, as we are using this I2C dev header file library, so within that we are initializing our wire.begin for I2C communication. This is serial.begin, and when serial is initialized, okay, so we are getting interrupt signal. We are getting interrupt signal from the user, and once interrupt is obtained, it will start reading the values. Okay, so this is all about setting the offset. Offsets are, I think, mentioned in the data set. We need to use those values. Okay, this is all initializing your MPU device. Setup is, and within loop various macros are defined. Okay, so it is it is reading the status of interrupt, and based on that the FIFO count, that it is initializing the FIFO count, first in first out. Okay, and based on that count it is giving you the error. So currently we are not using that one. Okay, we are directly going for this particular part. Okay, as this macro is uncommented, only this part will be executed. As I said, they have directly given us the values. So these are already the inbuilt functions, and we are accessing only those functions from the MPU.h, whatever is the header file corresponding to MPU we have added, and directly we are getting the values of yaw, row, and pitch in terms of angle. Okay, those values are converted into angle. This is how this code has been represented, where we cannot exactly get the idea how we are getting those roll and pitch, and that's why I just explained you the previous one. I'll now upload this code on the Arduino, and we'll see the same connections, only interrupt pin has been connected, and it is connected to the interrupt pin of your Arduino, which is nothing but digital pin number 2. Done uploading. So we will see the baud rate set here is 115200. Here we need to send a character to interrupt or to start your processing of that. Okay, so again the position is horizontal. Okay, and you can just, it's going very so while you are requesting something, I'm getting request to allow, that means the Suyash.
Sorry, ma'am, by mistakenly it was clicked. Sorry.
Yes, ma'am.
So this is these are the values. I'll just stop this one. You can see here yaw, pitch, and roll. So pitch and roll are almost we are getting, it is aligned to x and y plane. So we are getting those as almost 0, and yaw is also 0. Now I'll rotate that similar to about y-axis. Okay, I have rotated it about y-axis in the clockwise direction. So you can just see here, when I rotate this about y-axis, my yaw as well as pitch has changed, whereas raw, as we have rotated about y-axis, it is almost 0. Okay, now again I'll rotate same around y-axis, but in the anti-clockwise direction, 90 degrees. In the anti-clockwise direction, I'm getting that as positive. Okay, so pitch is positive. Yaw, actually it is depending on the position, it might be calculating yaw, but actually we are interested in pitch. Okay, so about y-axis, anti-clockwise, I'm getting this as positive values, and clockwise 90 degrees, I'm getting it as negative values. Okay, similarly now I'll move this one, your sensor about x-axis 90 degrees clockwise, and you can see here it is, as the position is not exactly stable, you can get that as almost closer to 90 degrees, but as it is clockwise giving you minus. I'll now rotate it about again x-axis, anti-clockwise 90 degrees. I have hold your sensor, so I'm getting almost 70. It will increase till it becomes stable. As I'm holding that in my hand, so it could not be stable, but you can just observe roll is changing according to the rotation. Yaw or pitch is changing according to the movement of that accelerometer around axis. Okay, now we'll show you the same thing in the processing software. For that, I need to just run this one. I need to close the serial monitor. It is closed. Okay, so I need to uncomment this macro, this function. Need to comment the Arduino code. Okay, and again upload this processor software onto the board. And this is this. This is done uploading. This is the processing software. So it is the software where you can simulate or you can see the behavior, how your component sensors are working. Okay, you can simulate your LED on off. Almost all components you can simulate on this processor ID. Okay, so again, this is the code which is taken from the MPU library examples MPU, and in that DMP6 processing, under processing you will find this MPU teapot, this code. Okay, and simply before executing this code, the teapot has to be compiled and uploaded through your Arduino IDE onto the board on the Arduino controller, and then you need to execute this code. Okay, so you can find this is what is representing your simulation, or this is what it will read the position of your accelerometer, and depending on the position of accelerometer it will start moving. Just a minute, it will work. Something. Okay, I'll execute once again. We will check here first whether we are getting that it is set to 1500. Now we have initialized. I'll close this one. It was waiting for interrupt actually, and now I'll run this. Okay. So this is the initial position. So it will take some time to become stable. So let it become stable, then I'll switch on my camera. I'll just adjust my PC first. Okay, now this is the position. I think you can observe both the screens. And according to the accelerometer position, so it is trying to stabilize itself. And once it gets stable, we will move our accelerometer. Okay, now you can see the position. It has become stable. I'll move this. See, as I'm changing the direction, so it is changing that figure, that so it's changing the angle as per the angle of this accelerometer. Okay, so this is how any object is trying to adjust itself based on the readings which are obtained from the accelerometer. Is that clear? Are you able to observe this video? The
Yes.
position of sensor. Now I just taken it upwards. Okay, so as we move this, your object is moving. So means this is how your motion sensors are trying, or these sensors can be used to just detect the current position and trying to adjust based on the accelerometer values. It will try to stabilize the position. Okay, so basically it may be used in robots. So this is all about today's okay, I'll just switch off this video. Okay, so this is all about today's practical and demo of that practical. If you're having any doubt, you can ask. So in this only you need to write the post-lab questions because we cannot simulate this one. I will share all these codes with you. You can go through that. And this is very useful sensor actually, almost in all the applications. Okay. Okay.
Okay, ma'am.
Then we will stop. If you are not having any doubt, again I'll create a folder corresponding to this second assignment, and in that only you need to upload is the post lab questions. Okay, you need not have to perform anything. For next two practicals, we require MATLAB. We are going to implement Simulink models of the MATLAB. One is cruise control and another is interior light control. Okay, and for that your MATLAB, I think everybody has MATLAB installed on your PC, and you might be knowing how to start with the Simulink. I'll show you how to start and build the model with Simulink, and rest of the things you can implement. Okay, so for today we'll stop here. If you are having any doubt, you can ask any time. And remaining students, those who have not uploaded, like Rohit Raj, Snehal, Pranot, and many more, okay, not uploaded the documents of first experiment. So they are supposed to upload the documents, implement on your own and upload your own documents. Okay, I'll stop. I'll end this meeting. Okay.